In section 1.2, we're going to be looking at something we call Cauchy sequences. But before we begin, he was a mathematician, Augustin Louis Cauchy. He was a French mathematician, and he did a lot of stuff. I remember learning in class about him in my complex analysis class, but also in abstract algebra and real analysis. So this guy, big mathematician, big name. So we're going to first define what a Cauchy sequence is. And we kind of built a bit of intuition last time by saying that seeing how convergent sequences the points would get closer and closer to each other. So in this case, we're going to define a Cauchy sequence to be a sequence A sub n. We're going to call it Cauchy if and only if for each epsilon greater than 0, there's a positive integer n such that m and n both greater than big N has the difference between a sub n and a sub m to be less than epsilon. Again, it looks, first of all, like the definition for convergence, for a sequence to be convergent. But there's a slight difference, and we're going to go over that difference because maybe you may not remember the definition for convergence. So I'm going to put them up here. A convergent sequence and a Cauchy sequence. So first of all, we both start off with the same thing. A sequence S sub n of real numbers and a sequence S sub n of real numbers. For convergent, we say it converges to a real number S. And here we just say it's a Cauchy sequence. With what condition? Provided that for each epsilon greater than 0, so still the same, there exists an n, so again, in convergence, n depends entirely on epsilon. Same thing here. There exists a number n, again, depending on this epsilon, such that, now here's the difference. On a convergent, we have to have n is greater than or equal to big N, such that the difference between the point after this n and the limit point, so the distance between those two is less than epsilon. So given an epsilon, given a goal, after a certain point, our points get arbitrarily close to that limit S. Now over here, we have both m and n greater than. We can have greater than or equal to, both definitions work. But m and n greater than n, so almost the same as convergent, implies that the difference between the 2 points here, notice how we no longer have S. We're not approaching the limit per se. But having m and n greater than big N implies that these 2 points are less than epsilon, meaning the distance between those 2 points get arbitrarily close. So a Cauchy sequence is a sequence that has its points getting closer and closer to each other. How close? Well, arbitrarily close. Given whatever epsilon greater than 0, we can still find m and n such that the distance between them is less than epsilon. That's what a Cauchy sequence is. Basically saying that the points get closer and closer to each other. And just like anything, a picture might be able to help. So here's the picture. Let's focus on the one on the left first for the convergence sequence. So for the convergent sequence, epsilon is this green area here. This is epsilon, right? I am not on the line, but that's epsilon, this green part, right? And our limit point is S. This is what we think it's converging to, this line. And notice how after this N, from then on, all the points, this one, so on and so forth, are within this green area. Meaning, given this epsilon, this is the n, such that any point after that, the distance between that point and the limit point is within epsilon, right? We are within our goal. Now, just before moving on, notice how these points, these are the ones that are not yet within epsilon, not within our goal. And what can we say about them? How many are there? Well, there are a finite many. There are finitely many from a lemma we learned last section. So now looking at this right-hand one, the picture for a Cauchy sequence, we have that S sub n, which is just a point. This point here, and S sub n, which is this point here. And again, epsilon is still that green area. The distance between these two is this right here. This is the distance between then the 2 points, and that is less than this epsilon distance here. Right, so they're getting closer and closer to each other. Notice how the further out we go, the closer and closer these points get to each other. Right, so here we chose m and n to be greater than what? This over here, than our n, such that these 2 points are close enough to meet our goal, to be the distance to be less than epsilon. That's what a Cauchy sequence is. That's the difference between a Cauchy sequence and a convergent sequence. But why do we care about Cauchy sequences? Why not just leave everything as it was? Well, we're going to try to visualize this. Right, so this is our limit point A, what we think it converges to. And let's say I'm just going to draw a random sequence. Here, dot, 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 dot. But after a certain point, remember they get closer and closer to each other. So I should draw this one over here more like. They get closer and closer to each other. So you would think that at some point here, there's going to be a bunch of little points. Maybe if we draw some neighborhood, maybe there's going to be infinitely many points somewhere there because they're going to get arbitrarily close. So now the question comes up, well, are convergence sequences Cauchy? And do Cauchy sequences converge? So we move on to a theorem, which says every convergent sequence is a Cauchy sequence. Right, so this proof isn't too long. We're going to suppose first that A sub n, the sequence, converges to A, and choose epsilon greater than 0, just as we do to prove convergence. And because epsilon is greater than 0, we know that epsilon over 2 is greater than 0. And we're going to see why we're saying this here. It's a bit clever, but we'll see the purpose of it. So there's a positive integer n, such that little n bigger than or equal to big N implies that the difference between the sequence and the limit point gets arbitrarily close. How close? Well, less than epsilon over 2. This is just given by our definition of convergent sequence, right? Because we're assuming A sub n converges to A. So then, if m and n are both bigger than n, what can we say? Well, that the distance between A sub n and A, our limit point, is less than epsilon over 2. Again, why? Because it's greater than, little n is greater than big N, or equal to, and m is also greater than or equal to big N. So the difference between a sub n and our limit point is also less than epsilon over 2. This means that if we have a sub n minus a sub m, well, here we're just going to add 0 in a sense, minus a plus a. But now we can use a triangle inequality to say, well, this is less than or equal to a sub n minus a plus a minus a sub m. And over here, because it's an absolute value, gives us some freedom to switch the terms around. So this here is the same thing as this. All we did was switch a sub m with a, right? Because it's in our absolute value. But now we can see something about these two terms, or the two expressions in the absolute value. We know that both of those are less than what? Epsilon over 2. And if they're both less than epsilon over 2, we can just add them to be both less than epsilon, right? For their sum to be less than epsilon. And what does that mean if they're both less than epsilon? That means that the distance, this distance here, gets arbitrarily close. A sub n and a sub m gets arbitrarily close, such that it's less than epsilon. Therefore, it is Cauchy. Right? So every convergence sequence is a Cauchy sequence. And now logically, what else can we say? Well, we can say that if a sequence is not Cauchy, then it is not convergent. Right? That's just a contrapositive. So next is a theorem that tells us that every Cauchy sequence is bounded. And I draw the line right here so that we can use it as a visual. I'm going to go ahead and erase everything. So every Cauchy sequence is bounded. This proof is really similar to the one showing that every convergent sequence is bounded. And here we're going to suppose a sub n is Cauchy. We're going to choose epsilon to be 1. Why to be 1? Well, just to choose a epsilon neighborhood, and you'll see why. So there's a positive integer n, big N, such that if m and n are greater than or equal to n, then the distance is less than 1 or less than epsilon, right? Because we're letting epsilon be 1. And that just comes from the definition of this sequence being Cauchy. Okay, so we're going to let m, it's right here, be n plus 1, which is obviously greater than n. So then a sub n, here we're just going to add 0 in a sense again, is equal to this, a sub n minus a sub m plus a sub m. Okay, so by the triangle inequality, that's less than this distance, a sub n minus a sub m, which we already know something about, plus a sub m. We can just plug in, because over here we know this is less than 1, so this one here, this here must be less than 1, that's why it's less than, plus a sub m. Right, and again we plug in for m, we let m equal n plus 1, so we plug it over here. But again, what are we trying to see here? It'll become apparent. But here we're saying that a sub n that point is less than 1 plus a sub n plus 1. And that just comes from saying here, this, which was equal to this, less than this here. And here is where, I guess, the meat comes in. We're going to set m, just as we had done in the proof for proving that every convergent sequence is bounded. We're going to set m to the maximum. And here's where I'm going to start drawing on the line to help with the picture. So we're going to draw points. I'm just going to draw first of all, I'm going to draw the epsilon. So this is, I suppose, just the distance of epsilon. Okay, and I'm just going to draw random points. So after a while, points in here start getting closer. And I'm not necessarily converging to any point in here, but points after a certain point are the distance between any 2 points here is within epsilon, meaning that the distance is less than epsilon. That's why I'm drawing them closer to each other here. So as to not confuse you, maybe it's better to draw epsilon. Let's say epsilon is this distance here. This is epsilon. So after a certain point, they get closer and closer to each other. How close? Well, less than epsilon, no matter what epsilon is. Okay, so if m is the maximum of these absolute values, of the absolute values of all the points, well then, we can draw, say for example, this was the maximum, we can draw our, so this is m, and I suppose this is negative m. At that maximum, all the points will be within that interval, right? Meaning that this m is our bound, it can be our upper bound and our lower bound, because, well, they're all absolute value, right? So all these here. And this absolute value, you may want to try this proof without using absolute values, and you can follow the steps of the showing in the last section that's showing that every convergent sequence is bounded, because this here does converge. This here does confuse many students, saying how a single number m bounds absolute value of a n of the sequence. But the idea is the same, and it shouldn't be too hard to prove without the absolute values. So this shows that every Cauchy sequence is bounded. We knew that every convergent sequence was bounded. Now we know that every Cauchy sequence is bounded. Right, so now we come up with we present a definition of an accumulation point. What's an accumulation point? Well, we're going to let set S be a set of real numbers. And a real number A is an accumulation point of S if and only if every neighborhood of A contains infinitely many points of S. And we haven't gone over examples yet because it's mostly just been theorem proof. But we're going to go over examples of what accumulation points are. So given the set, the open interval 0, 1, what are the accumulation points of, well, the open interval 0, 1? If you want, you can go ahead and pause and think about it. Use that definition above this. So, okay. if you came up with the closed interval 0, 1, congratulations. If you didn't, let's see why that is. So first we have, I'm going to draw the open interval 0, 1, and obviously all the numbers between. So no matter what point we pick, say this point, no matter what epsilon neighborhood I draw, there's always infinitely many real numbers close, arbitrarily close to, or within that epsilon neighborhood of that point. There's always an infinite amount of them. But what about 0 and 1? Why are we including 0 and 1 for the accumulation points? Well, if we draw a point at 0, if we have that point, no matter what neighborhood I draw, I'm just going to draw a bigger one for the sake of being able to see this. We have no points on this left-hand side. But on the right-hand side, no matter how close you get, closer and closer, there's always an infinite number of points close to 0. No matter what epsilon you choose, there's always an infinite amount. And that's the condition for the accumulation point. An accumulation point is if and only if every neighborhood of A, in this case 0 being our A, contains infinitely many points of S. It doesn't necessarily say infinitely many points on both sides if we're on the real line. It just says infinitely many points of S. And in this case, well, 0 does have, any neighborhood around 0 does have infinitely many points of S. So let's try another example. What about the integers? If our set S is the integers, what is the set of our accumulation points? Again, go ahead and pause it if you want. Think about it for a few seconds. Okay, if you got that the set of the accumulation points is the empty set, congratulations. If you didn't, let's see why that is. So I'm just going to draw, let's do 1, 2, 3, 4, so on and so forth. None of these are accumulation points. Why not? Well, remember, every neighborhood of these of the points has to have an infinitely many points of the set S, which are the integers. And sure, the integers are infinite, but if we draw, let's, for the sake of this example, let's choose 2. If I draw this neighborhood here, well, there are no points in that neighborhood other than A. Right, so in no way does that have infinitely many points in that neighborhood. Same thing with 4, or actually with any integer. I can draw a epsilon neighborhood, and it contains no points. So the set of the accumulation points is empty. Last example for accumulation points is a set, or the sequence 1 over n. What's the accumulation point here? Go ahead and pause again if you like. Okay, this one may be a bit tough, but the set of the accumulation points consists of only one point, and that point is 0. And just remember, there's a big difference between empty set and 0. 0 here is a point, right? Because if we have 0 here, let's say this is 1/2, 1, 1/3, 1/4, so on and so forth. We know, first of all, that this sequence S converges, right? And what that means is that these points are getting arbitrarily close to 0. And this really comes from showing that 1 over n, the sequence, does converge to 0. That no matter what epsilon, remember we said no matter what epsilon we choose, there will always be another point that's close to 0. So there's infinitely many points close to 0, and they're getting arbitrarily close to it, right? But no other point is an accumulation point. If you were to pick, say, 0.000 with maybe a million zeros, and then 1, 4, 2. Maybe that's a point in our sequence. We can still find a epsilon neighborhood around that point such that there are only either finitely many points or no points in that neighborhood. So in this case, only 0 is an accumulation point. Okay, we move on to a lemma, which says let S be the set of real numbers, then A's accumulation point of S if and only if each neighborhood of A contains a member of S different from A. So what is that telling us? That's just telling us that every neighborhood has to have another point for it to be an accumulation point. And again, this example I was talking about, sorry, ignore the question for now. But this example I was talking about, this being 0, 1, 1/2, so on and so forth. No matter what epsilon neighborhood you draw around 0, there will always be at least one point closer to it. And that again, that we know that because this sequence converges. So then the question comes up, is the limit of a convergent sequence always an accumulation point of the range of the sequence? So go ahead and, if you want, read that sentence again. Read the question, and what do you think? Is the limit of a convergent sequence always an accumulation point? Well, the answer is no. But can you come up with a counterexample? A counterexample would be the sequence, the constant sequence of all the points being 1. Right? So I'm just going to draw a number line, -1 and 1. All the points are 1, and then 1 again, and then 1 again, so on and so forth, infinitely, right? For infinitely many terms of the sequence. So it's just 1. Right? And if we draw a neighborhood around there, well, it's not an accumulation point because there are not infinitely many members in that neighborhood. Right? So that is a counterexample, even though over here we were led to kind of believe that the limit of a convergent sequence was was always an accumulation point. Well, in this case, it is. It is here, but not in this case over here, which is a counterexample. So we come up with the theorem, and over here, this lemma isn't really, I guess, central to our lesson here of Cauchy sequences, but it's a good thing to know and keep in mind. So now theorem comes up. Every real number is an accumulation point of the set of rational numbers. Why? Because given any real number, there's infinitely many rational numbers or arbitrarily close to that real number. And the same thing for the irrational. Every real number is an accumulation point of the set of rational numbers. Again, given any real number, I don't know, say pi, there's an infinite number of rationals and irrationals close to pi. Arbitrarily close. So can a finite set have any accumulation points? Well, that's an interesting question. And this one's pretty simple. You can think about it. I'll give you the answer. It's a finite set can't have accumulation points by definition of accumulation points, right? We need to have infinite number of points in a neighborhood. But this next question is interesting. Under what conditions can one guarantee that a set will have at least one accumulation point? I'll leave you to think about that one. But now we come up with a theorem so important, it has a name. So just like the Pythagorean theorem that has a name, theorems with names are usually really important. Or it's just It's an amazing proof, so to speak. But before that, I'm just going to mention it's named after these two mathematicians, Bolzano and Weierstrass. That's why it's called the Bolzano-Weierstrass theorem. And I would encourage you to look up more information about them. It's always interesting to look up people and know their motivation and how they came up with this theorem. This theorem's really important, but the proof would take me at least 20 minutes. So I'm just going to give you the intuition for this proof. And this proof says, or this theorem says, that every bounded infinite set of real numbers has at least one accumulation point. Right, so if we have every bounded set, I'm just going to draw bounds. These are the bounds, right? And inside those bounds, there are infinite points. Right? We don't know how they're scattered necessarily, but we know that inside those bounds there are infinitely many points. So it's a bounded infinite set of real numbers. And they claim that it has at least one accumulation point. So the intuition behind this is saying, hey, let's cut this in half. And either this half here or this half here has an infinite number of points. And why is that? Well, because if they both had a finite number of points, well, then this whole thing would be a finite number of points. It would only have a finite number of points. Therefore, at least one of these has to have an infinite number of points. So let's say the left-hand side here is the one that has an infinite number of points. So we focus on this one. And now what we do is we split it in half again. Now at least one of these has an infinite number of points. Again, because if they didn't, then we would only have a finite number of points. So let's say this half is the one that has an infinite number of points. Can you guess what happens next? We cut this in half. And again, one of these two halves will have an infinite number of points. And then we cut it again. And so on and so forth. It's a sort of nesting iteration that we do, which will eventually get to a point, right? If we continue this infinitely, we'll get to a point. And the proof is really interesting. But it is really lengthy. That's the intuition behind this. Always choose the half with an infinite number of points. And you'll get closer and closer to that point. That is the accumulation point. That's how we can guarantee that a bounded infinite set of real numbers has at least one accumulation point. Okay, and on the last slide, as you can see, we're going to have a pretty big proof, but it is a juicy one. But before we do that, we have some yellow boxes to go over. So we're just going to review. We know that every Cauchy sequence is bounded. We know that every bounded infinite set has at least one accumulation point by the Bolzano-Weierstrass theorem. And the range of a Cauchy sequence can be infinite. Right? That one's probably the most obvious. What else? If a sequence A sub n is Cauchy and its range is finite, then the sequence is constant from one point on, and therefore converges. And we saw that in the example where we just had the constant sequence 1, right? The range was only finite. It was only 1. That was the range. But if it's constant, well, that means it converges to, well, that constant point. Okay, so now we mentioned the theorem. Every Cauchy sequence is convergent. Remember, we had proven that every convergent sequence was Cauchy, but now we're saying every Cauchy sequence is convergent. And again, a little picture to help us. So we start with letting A sub n be a Cauchy sequence. And again, as I mentioned, if the range is finite, the sequence is constant from some point on, therefore it converges. So we took care of that example, that case, right? If the range was finite. But what if the range is infinite? Well, let's suppose the range is infinite, and we'll call the range S. By our previous theorem, remember over here, I'm going to circle it in red up here. We showed that every Cauchy sequence was bounded. So by previous theorem, S is bounded, right? Because it's a Cauchy sequence. And therefore, by the Bolzanovistra theorem, S has an accumulation point. And we're just going to call it A. Why? Because, again, we have a range that is infinite and it's bounded. So the theorem tells us that there's at least one accumulation point, and we're going to call it A. Okay, we're going to show that this sequence converges to A. So we choose epsilon to be greater than 0. Right, and before we go on, I'm going to draw this A here. And actually, I might need a bit more space. So I'm going to do this over here and this over here. And this is A minus epsilon over 2. And this is A plus epsilon over 2. And this is neighborhood of A. And it contains infinitely members of the set S. And again, because our accumulation point here is A, we know that this neighborhood of A contains infinitely many members of the set S. The set S can be something like this. This can be S. But we know in that neighborhood of A, there are infinitely many points. Okay, well, since A sub n, the sequence is Cauchy, there's a positive integer n such that after that big N, the points get arbitrarily close, meaning after a certain point, our points are closer than the distance from A to A plus epsilon over 2. They could have been over here. It doesn't matter. But just after a certain point, they're closer than this distance here. Right, so that's why I drew those 2 points close to each other, here and here. They get closer than epsilon over 2. Also, because this neighborhood of A contains infinitely many points, and hence infinitely many points of the sequence A sub n, there is a number, we're going to call it n naught, such that after that point, or that point is within that neighborhood. And why is this important? Well, we're going to be a bit clever here. If n is greater than that n naught, we can have that the distance between that an and our limit is equal to this. And here again, we're adding 0 by adding this little point here. So that is less than or equal to, we're using the triangle inequality, then A sub n minus A sub n naught. Actually, I should put, let's draw it right here. This point here is n naught, A sub n naught. This one was A sub m and A sub n. So by the triangle inequality, we know that the difference, or the distance between A sub n and a sub n naught plus a sub n naught minus our limit point is less than or equal to this over here. And again, by a triangle inequality. But what do we know about this? Oh, sorry. What do we know about this distance and this distance? Well, they're definitely both less than epsilon over 2. Right? And if they're both less than the sum of epsilons over 2, well, they're both less than epsilon. And what did that tell us? Well, that points get arbitrarily close, right? And that this distance here, a sub n minus a, is less than epsilon. By definition, the sequence a sub n converges to a. So what did we just show? That every Cauchy sequence is convergent. Now, to end this, we come up, I present to you our punchline. A sequence is Cauchy if and only if it is convergent.